The key to understanding radicals is understanding how to simplify radicals. And we simplify radicals by factoring out a perfect square. What are perfect squares? Perfect squares are numbers that you can take the square root of and get a whole number. Like 2 times 2 is 4, so that makes 4 a perfect square. And I can take the square root of 4 to get the whole number 2. So when it's underneath the radical, it's called a radicand. So inside the radical symbol is 4. But when I take the square root of 4, it becomes outside, which is 2, no longer needing the symbol. The next perfect square would be 3 times 3, which is 9. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. The square root of 36 is 6. And so on and so forth. You can list your perfect squares. We talk about perfect squares because when you rewrite a single radical as a multiplication statement of 2 radicals where one of them is a perfect square, that's how we simplify. So the first step to simplifying is rewriting the radicand as 2 factors, and one of the factors is a perfect square. So oftentimes you can use the square root of 4, the square root of 9, the square root of 25 as your perfect squares. So you just want to say, is 52 divisible by 4? And it is. So I'm going to break this down as the square root of 4 times what? So 4 times what is 52? So if I divide 52 by 4, I get 13. So this would be the statement where I've rewritten 52 as 2 factors where the perfect square is 4. I could take this one step further and actually simplify. So the square root of 4 is 2. So that's how 2 becomes the outside number, and the square root of 13 is left inside. So this would be considered the simplest form of the square root of 52 because you can't go any further with 13. It's not divisible by a perfect square anymore. It's not divisible by 4. It's not divisible by 9, and so on. We can do a similar problem here, the square root of 80. 80 is divisible by 4, so I'm going to rewrite it as, sometimes they just use one line and then just put the multiplication under here, and that's fine. 4 times what is 80? So 80 divided by 4 is 20. So that is a product that multiplies to give 80, and one of the factors is a perfect square. If we went a step further, the square root of 4 is 2, so it earns its way outside. When you take the square root of 4, it becomes 2. Now it's an inside number. So 2 square root 20. However, that one's not in simplest form because 20 is still divisible by 4. So I can do it all over again. The square root of 20 is 4 times 5. I can replace 20 with 4 times 5 and then leave my 2 outside. So again, I've rewritten 20 as a product of 4 and 5. The square root of 4 is 2. So that 2 is going to come out and be multiplied with the other 2. So I'm left with 4 square root 5. Now, I could have gotten this from the original problem by taking the square root of 80 and knowing that 80 was divisible by a bigger perfect square, which is 16. 16 times 5 is 80, and the square root of 16 is 4. So 4 square root 5. So I could have gotten it in one step, but a lot of times we don't always know the biggest perfect square that divides into something. So as long as you just can continue when your inside number, your radicand, is still divisible by a perfect square. We also simplify with variables. Anything that has a even exponent is a perfect square. because when you multiply x to the first times itself, x to the first, you add the exponents and you get x squared. So the square root of x squared is x to the first. Well, the next biggest exponent is 2, and when you multiply x squared times itself, which is what taking square root means, you get x to the fourth. So the square root of x to the fourth is x squared. When you multiply x cubed times x cubed, 3 plus 3 is 6, you get x to the sixth. So the square root of x to the sixth is x cubed. So basically with exponents, it's what plus itself equals 10, because the rule for multiplying when you have exponents is keep the base, add the exponent. So the square root of x to the 10th is x to the 5th. Because x to the 10th would be considered a perfect square, and x to the 5th times x to the 5th is x to the 10th. Odd exponents always have an odd one left over in the Radicand. Always. So then you know you've got 1 less than 15, which is x to the 14th. So basically I'm rewriting this as, here's my perfect square because it's an even exponent, but then here I have an odd man out. And the square root of x to the 14th is x to the 7th. So this would be the simplest form for the square root of x to the 15th. Simplifying is very important for adding and subtracting, because the one thing that you're going to want to do is just to add and subtract the numbers, but that's not okay. You have to have the same Radicand, meaning you have to have the same inside number. So you could add something like 5 square root 2 plus 3 square root 2 equals 8 square root 2. You cannot add 5 square root 2 plus 3 square root 5. You can't add that. That's like saying 5x plus 3y. They're not like terms, so you would have to stop there. You can't simplify that any further, and you can never just add and subtract the numbers underneath the radical. You always add and subtract the outside numbers when they have the same inside number. So I have to simplify. The square root of 27 is the square root of 9 times the square root of 3. That's equal to the square root of 27. I picked 9 because it's a perfect square. Remember, 4, 9, and 25 are the very common ones you can use the majority of the time. So the square root of 9 is 3, left with the square root of 3. So I have 3 square roots of 3 minus just this 1 square root of 3. Now I can add and subtract because they have the same inside number, and I only add and subtract the outside numbers. 3 minus 1 is 2, and keep the square root of 3. This next example is very different because you do want to recognize perfect squares. So if you need to use a calculator to recognize them, that's fine. You'll recognize them when you can take the square root and get a whole number. So what is the square root of 81? It is 9. What is the square root of 16? It is 4. But don't forget, you already have this negative 3 right here. And anytime you put a number right up against a symbol, it means multiplication. Multiplication comes before addition. So negative 3 times 9 is negative 27. And negative 27 plus 4 is equal to negative 23. So that would be your final answer. So you didn't actually have to simplify because you were able to just take the perfect square since they were both perfect squares.